Saitta, and I'm a faculty member in chemistry at the University of Central Florida. And today I'm going to be talking about STEM course planning for active learning. So when I think about active learning, I think of sometimes how it can feel like a glass that we keep trying to stuff more and more things into. Because a lot of times, although active learning can very well be done online, what I'm talking about right now is in the context of face-to-face classes. And so it almost seems like when you're trying to modify your class and trying to incorporate active learning, it could seem like you're taking a class that already has something that you plan to do or that you're already doing, and that your active learning is feeling like it's something on top of something that you're already doing, and it's just and nothing. And the more and more you put in it, you're just not going to be able to fit everything if you just keep adding to it. So the idea here is that what course planning can do is help you rearrange how you put your course together, and so you can put your active learning in where it needs to be and then fit the other stuff around it. Raise your hand if you've ever seen like a live demonstration or a video demonstration of this like sand in the vase thing. Yeah. So I saw this actually at a conference one time, and I hadn't seen it all the way since I was an adult, and I was like, oh, that's a really good analogy. So I think, though, that it fits really well here, because if you just take what you're already doing and put active learning on top of it, you're just going to be frustrated because you're not going to be able to do everything that you want to do. So that's the focus of today. So with that, I think that it would be a really great idea to start with an example. And so I have a little worksheet. I think I have enough. Hi, come on in. Actually, if you'd like to sit at this table, we can work in pairs. And I think this can be helpful because not only now do you get to be a participant, but you're going to kind of take it in the mindset of a student. So imagine now that you are a chemistry student and you're walking into a chemistry lab and you see two liquid samples in graduated cylinders, and your lab partner takes the mass and the volume of the individual liquids before mixing the two together in a beaker to form a homogeneous mixture. So what I want you and your partner to do right now is to categorize these things right here. So the mass of the mixture, the volume of the mixture, the density of the mixture, the identity of the mixture, into whether or not you think you would know that or not know that. So you're walking in, you have two different liquids. Once you mix them together, what do you know and what do you not know of those things? Okay. And so if you are somebody like a chemist who this comes right away, you can have your ideas, but also be mindful that most of the people in this room are not chemists. So you add the two liquids together and now it's a mixture. What do you know and what do you not know? Yeah, so if you can also anything else.
Oh, I can't pour it out of the beaker.
Just looking at it. So I'm going to pause right here. I understand that you are there were still some that you probably haven't talked through yet, but I just love to see where we are as a group. So how about this first group here? Was there one that you feel like both of you came to an agreement, whether it was known or unknown? You know the mass. Okay, so the group. Was there another group that said that they put the mass as in the known category? Okay. What about the total volume of the mixture? Did anybody would like to decide on where to put that? No. Okay. Why did you say no, Kirsten?
No.
Oh no. Okay. So why did you say known?
Right now, I would say we don't even know the math because we don't
Okay.
know the size of the beakers or anything like that. But let's say we do. Let's say they have the measurements on there, and we can take them. If we can figure out the mass, then we should be able to figure out the volume.
Okay.
It's just going one step further. And if I can recall math that long.
Yeah. Okay.
I think you're then adding 3 dimensions in there rather than 2. I'm humanities. Don't judge.
No. And I should have made a better point to say that all of these ideas, these are the kinds of things that I want to know. I want to know what you're thinking, and I want to know where your thoughts are. And this is actually the thing we're going to look at today. So it's okay if you don't know, if you guys aren't all on the same page, because we're all hopefully at the end going to be on the same page. Yes.
We started there, and then we thought, wait a minute, we don't know what these liquids are, and there could possibly be some sort of a reaction once we put them together. where
Or
the
different
volume-
intermolecular forces might result in a slightly smaller volume.
Okay, so the fact that we don't know what they are leads ambiguity to the problem too. So if maybe we could be more confident in what we would say if we knew what they are, but because we don't know what they are, then we don't know. Now, which ones are the ones that you say you don't know for your group?
The other two.
The volume's possibly known, but could very well be unknown, and then we said the density and the identity are definitely unknown.
Okay, so then your group said the mass of the mixture was known?
Yes.
Okay, awesome. Okay, so I'm going to pause here just for a second and say these are the kinds of things, this is, if we were going to do this in the classroom, this would very much be similar to what we would want. Hello, welcome, have a seat. How we would be interacting with our students and the types of questions we would be having with our students. So the key question that I want to bring up to focus on here is actually for that second category on that list, which is about the volume. So the question here is the volume of a mixture always the same as the sum of the individual volumes? So we heard from a couple of the groups saying, well, we don't know, or some people said, well, it depends on what it is. So go ahead and with your partner, why don't you write your beginning ideas on your worksheet. And so what do I mean by beginning ideas? I mean, what's your gut feeling? So I'm not saying you have to know the answer. This is not an answer that you're going to submit and it's going to be graded or that you're 100% sure. This is just, I want to know what you're thinking. So what kind of previous knowledge or experience, how could you answer this question? What kinds of things could you do? What kind of data could you create? So write down some things about what you think about that key question, some of your beginning ideas on your worksheet. And it could be like bullet points. It doesn't have to be full sentences. And we're going to go to the next part of this activity. So this activity that you're doing right now is actually the activity that we do the very first day of our Chem 2 labs at UCF. And so part of this activity is getting students an awareness of the kinds of things that we're going to do every week. So every week they're going to be doing a worksheet-led questioning like this. And so, but on the first week, we don't have safety attire, and so we're not able to work with chemicals. So the thing that we do next is we use a video that shows somebody actually demonstrating one way that you could answer this question. So the students after the first week would be then given tasked with creating an experiment and carrying it out themselves. But that's another reason why I picked this activity for this presentation, is because you could do this same activity with a class of like 450 students and they don't have to be in a lab. And so even if you're not a scientist, you can still kind of take this idea of if I have these large classes or if I'm teaching in an environment that's not ideal for what I really want to do, is there ways that I can use technology or something where I can simulate that same experience or simulate that same thought process? So what my students do next is they write down the tests, which is the procedure. In this case, it's not themselves that's doing the procedure. They're going to be watching someone else do it. And then they write down what happened in their observations. You're welcome to do that. I'm not collecting these, but if you were a student in my class, this is what you would be asked to do. But we will go ahead and just watch the video. The audio, as you saw from the keynote, is not hooked up. And so I will go to play this, and I can talk over it as she's going. So you can hear it? Okay.
Where you get to exercise your science brain, and I get to crank up the chemistry. Nothing says chemistry like a bunch of beakers filled with mysterious fluids, right? Okay, check this out. I want you to fill each of these beakers with water to exactly the same level. Next, I'll mix them together in this graduated cylinder and set that aside. Now I'm going to repeat the process, but this time I'm going to fill one beaker with water and the other with pure methanol. See, they're exactly the same level. And in a moment, I'll mix them together in a graduated cylinder, the same as I did.
Okay. So then this is where the video stops and the students would write down what they see. Now, if you're a chemist or even a lab or a scientist who have spent some time in a lab, you would see that this video is not perfect for a lot of reasons. one measuring in a beaker. We're going to get to that in our class later on in the semester, but for the sake of this activity, I think it's still an effective way to show the students what's going on. So this video would stop here, and the students would write down what they did. So then this is where I pause, and I have the students predict what they think. And so that's what I'm going to ask you to do here. You do not have to agree with your neighbor, but go ahead and at least have some kind of opinion or prediction as to what you think will happen. Remember I showed you the slide of the rocks and the sand and the different way that it arranged changed the volume? That concept is what's happening with these molecules here, where you have one beaker with the molecules on one size and another beaker with another on that size. When you mix them together, it doesn't just add on top of each other. The way that it's arranged actually affects the volume. And the identity of what those molecules are will change whether or not it's greater than, the same, or less than. And so the students then will write down what happened. This is clarifying what exactly is evidence, what exactly is a claim, and then they'd be prompted to write what their claim is. If you look further on in the worksheet, you'll also see that there's a place for them to reflect on how their ideas did or didn't change and why. And that's an important part of the process that will be continuing throughout. I think it might be on the very end, after the claim, on the last page. So number 9, it says, how have your ideas changed, or how have they stayed the same based on the data? And so this is something that they not only do this class, but they do in subsequent classes. So now that's the end of this activity. But the reason why I wanted to give you this activity first is so that you kind of see where I'm coming from when I'm looking at how do I design active learning activities for my class. So let's think about some of the valuable aspects of the lesson. One of them is that it's objectives based. So if you look at the beginning of the worksheet as well as the end of the worksheet, you'll see that there's very clear objectives that this activity is based on. I think that's like kind of key for creating a good active learning lesson, is knowing why you're doing it and what you're expecting your students to do at the end. The other one, I don't know how many of you use or know about the science writing heuristic. It's something that's pretty prevalent in chemistry, especially when you're doing inquiry-based labs. But that's one of the models that we use in this particular format. And so if you're interested in this process, it was definitely not mine. I adapted it from the science writing heuristic, which is what takes you through those steps of a key question and a claim and renegotiating what you originally thought. This promotes inquiry-based thinking. This activity may be less so than the future actual labs that we would be doing, but this is setting the students up for progressing through those types of activities when they're in the lab. And then another important thing, I think, especially if you were at the keynote yesterday, is like the idea of starting with the students' preconceptions. Because we're taking a really constructivist approach here, where we're not assuming these students are blank slates. Even from what the speaker earlier today was talking about, is that we have to think of the student holistically and think about what their experiences are and where they're coming from, and allow that to shape what their ideas are. I had a really great discussion one time with a group of grad students where we were doing a similar lab, and they were debriefing, and we were going down the line, and I asked them to summarize what they thought. And I got to this one student, and he's like, well, do you want me to tell you the answer, or do you want me to tell you what I think? And I was like, oh, how is that different? Like, tell me, like, what's the difference? And I meant it honestly. It wasn't like I was trying to belittle him or point out that he didn't know something. But I think if you come to your students like authentically curious as to what they think, they're going to be more willing to share with you what they think. And you need to make sure that that environment is such that students can be incorrect and still be progressive to their learning. So it actually helps their learning even if they're incorrect. And this is also, there's a paper that came out, I'll share with you in just a second, a slide that was talking about, so there's a concept of transfer in STEM education where if you learn something in one context, are you then able to do it again if the context is different? And that idea that learned information or processes can be transferred. The thinking process that's associated with that was already kind of implied by how my lessons were set up, but after reading the article, I'm being a lot more explicit about how I'm doing that. Collaborative group work, which our speaker was speaking about earlier, Oh, did it not? Okay. Well, the last one that I had on here that I thought was up, but it's not, is also universal design for learning. So that's another part. Raise your hand if you've ever heard of universal design for learning, so UDL. The idea here is to try to make our classes as accessible as possible for everyone. So that includes people that might have different types of accessibility needs, both visually or audibly. But then also things like having executive function disorders or different types of needs that based on the autism spectrum or something like that. So having a guided worksheet like this that helps give concrete prompts, or being able to organize graphically like in the known and unknown, all of those things you can do can help make it more accessible to all of your students. So this is it's called Thinking Processes Associated with Undergraduate Chemistry Students' Success at Applying a Molecular Level Model in a New Context. And so this is kind of the key finding from that study. And basically what they did was they started with 28 students. And I know the sample size isn't very big, but I think the way that the study was designed really gave to some results that can be pretty impactful. Is that they looked at the ones that constructed models consistent with evidence. And then this is all during their lab. And then in the interview, they tried to see if they could take what they were supposed to have learned and apply it in a new context. So out of the 28 students, 9 of them weren't able to do this in the lab. And so none of them were able to, in the interview, transfer it, which would make sense. They weren't able to do it in the lab, then it makes sense that they wouldn't be able to do it in the interview. So the 19 students who did do it, some of them, or all of them, were asked to explicitly engage in accurate metacognitive monitoring. And the 7 students that weren't able to do that, only 29 of them were able to transfer during the interview. But for the ones that did, then all of those students were then asked to explicitly use evidence to justify a model refinement. And for the 3 students that didn't, then only 33 of that population were able to transfer. But for the 9 students that did, 100% were able to do that. So it's kind of like showing the importance of these different steps and holding students accountable for being able to do that and giving them feedback on when they do that and when they aren't doing that correctly, in the hopes that then they would be better able to use that information that you're trying to teach them in a different context later. So with that being said, this is just one type of example. I tend to use a lot of inquiry-based instruction in my own teaching. Let me see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I don't have quite enough for everybody, so why don't I hand them to the same groups? And if you want a copy of this, I'm happy to share with you electronically.
I don't need whatever.
Okay.
You should have 10.
Yeah, okay, well, thank you, Kevin. Here you go. Yep. So this is a handout that I made just to kind of navigate how you can go about making inquiry-based activities for your STEM classes. And I think one of my favorite things about this is this table here that I am taking from Michael Abraham, who wrote a chapter of Chemist's Guide to Effective Teaching, the original one that came out, or the first version that came out. And so the reason I think of this is I do have some colleagues that still question the relevance or the need for inquiry-based learning, or why I have a class that is entirely inquiry-based learning. And my argument is I don't think that everything needs to be taught through inquiry-based learning, but the focus of what I'm trying to teach my students in this class for what they're learning, that is an appropriate instructional tactic. But here, like, there's other things that you'll need them to learn. So, like, again, I teach a lab, which is the context of what I'm talking about now. But like, if I'm going to show that they need to do a titration, I'm not going to say, figure out how to do a titration. No, I will demonstrate how to do a titration, how do you use the laboratory glassware and all those things. So it really just depends. Like, I guess the point here is I'm not saying take what I'm doing and saying directly. You really need to think about what is it that you want your students to know and do and perform, and pick something that makes sense for them. And so if it is inquiry-based learning, which is really good with teaching concepts. So here, the example is conservation of mass. the concept that we were debunking with that first activity was that even though the students know the conservation of mass, meaning you have a mass of this and a mass of this, and when you combine them, they're going to have the same mass. Even if you have a reaction, if you have all of the reactant or all of the products, it's going to be the same mass. Students are smart and they learn that, but then they incorrectly carry that through to volume as well. And so it makes a lot of sense that someone who's really good at chemistry and even really good at science would just carry that through to the wrong unit. And so the concept that that is not carried through to volume was the key part of that first activity that we did. Any thoughts or questions on this part? You can take this with you. It has some more strategies on if you're interested in getting started with inquiry-based instruction. You're welcome to look at that a little bit closer. But like I said, this is for my classes, and what I really wanted you to do was to look at what makes sense for your own classes. So, that's the wrong one. So this other handout is really supposed to be, no matter what you teach, no matter what discipline really you teach, this should be a guide that can help you plan. Mm-hmm. So, let me see. You'll notice on the worksheet that the first thing that you're going to be asked to think about are what are your objectives and how are you planning on assessing your students. So this kind of is a nod to backwards design where you think of the assessments first and you work your way backwards to what you're going to be doing in class. And so I mean, this is a really great way to start. If you're going to be rearranging that vase with that sand and the rocks, like I mentioned before, the rocks are what do you want your students to know and do at the end of this whole learning process, and that's what we need to put in first and then arrange everything else around that. So why don't you go ahead and think about something that a class or a topic or even a lesson that you would want to incorporate with active learning. I'll give you about a minute just to think on for your own. This isn't necessarily a group work, but just think of something, because then the rest of it, I want you to think of that particular lesson or topic for the rest of the questions. So I would love to get a feel about what kinds of questions we'd be thinking about or what kinds of topics. Would someone from this table like to just say at least what topic they would be wanting to do active learning with in their class? Did you pick one?
I'm thinking about, I have to teach like kidney functions, so I'm thinking about that.
Yeah, kidney functions, great. I know nothing about that, so I would love to be in your class and do some kind of activity on that. Did you have one that you thought of?
Think about conflict management.
Conflict management. So that would be something that the students would have to be mediating conflict, or they would be in the conflict and they would have to manage it like as a participant?
I think we've done it a couple of different ways.
Mhm.
I think how to do it even better.
Yeah.
Where because there are different types of conflicts, some through emails, we have like
Yeah.
electronic conflict and how
Cool.
to manage that, as well as some, we're nursing, so bedside
Yeah.
conflict.
That sounds like, that sounds like a great place for active learning too. Right away I could think of like case studies or even like role playing, that kind of thing. Or even, yeah, that's great. One of the things that I love that you said is that we do it in different ways, but I'd like to make it better. And I think really that's where I think all of us are, because you guys are the ones that are at an active learning expo, right? So it's like you guys are already the ones that I'm expecting are already doing great active learning things in your classroom. But I think that's an important thing, is to think like, well, how can we make it better? How can we take this one thing that's not really working and make it work better? Yeah, we're on the same page. Awesome. How about from this table?
I'm doing this new gen ed class on physics of energy and the environment, so it's non-science majors.
Okay.
So no lab.
Okay.
The topic I put down was power density of solar photovoltaic
Cool.
installations.
So audience here is really important, right? You need to know who your students are, because how you're going to have to sell it or get their buy-in is going to be different depending on who your audience is. I think that's a great point. And then also, it sounds like, I don't know much about your topic, but the fact that it sounds like something that could be really relevant even if you're not necessarily going to be a physics major.
That's the idea.
So I think you're spot on there. Great.
I did the structure of the cell membrane and how the chemistry is related to function.
Oh,
Because they
great.
can memorize the pieces, but then how does it actually all come together and actually work? So
Wonderful. Great. So the next thing that I'm suggesting is to think about the things that are easy for the students or for you to do outside of class and move it to outside of class. To me, for my own lessons, it doesn't make sense for me to lecture them about things that are already in the book because I feel like they could do that outside of class. I don't want to spend class time with this. And I work with a lot of faculty and experts that are really focused on online learning. And the question comes up is, why do we even have face-to-face classes? I mean, that's a legit question, right? If we can do all of this through technology, why do we even need to meet? And I think that question right there really does drive what I'd pick for active learning. And so if you want to pick things for your active learning that make it a good reason as to why they're there, because you just like telling them things is not a good reason for that. So that's where I say move things that are easy for the students to get kind of without your help outside of class. Does it make sense for you to emphasize things or clarify misconceptions? Sure, of course. So I'm not saying don't lecture to your students or don't talk to them about the content in the book. I'm just saying think if there's a thing you think they can get on their own, do that. And then the other thing where it says or for you, like quizzes. If like for me, my pre-lab quizzes, I just have them online because instead of having them like in class, just the way for my students and for my students' needs, it makes sense for them to just do that online before they come so I can have more time in class. The other one is target areas of misconceptions or struggle. There's a type of, I guess, I don't know what it's called, category in chemistry that we use a lot called discrepant events. And a lot of times if you see people like, I don't even know if you guys feel like this, but if you think of chemistry, people almost think of like a magic show. They're like, oh, chemistry, like the color change. And it's like, why do they like that? It's because something different than they expect happens, and that makes it interesting. So if you can find places where people go, wait, what? Wait, why does that happen? That's what you want. Because if you can have a whole room of like 50 or 250, 500, depending on who you teach, 30, if you have a bunch of the students looking at you saying, wait, why did that happen? I mean, you're ready to go in terms of teaching and learning. So that idea of working with someone where they have misconceptions. Another thing is working where they struggle. You've been teaching a long time. You know where the students are going to struggle. So pick that as your area for them to do the active learning, because them doing that with your here and with their peers, that's where that can be the most powerful. Oh, that should be either. Sorry, not wither. Design an activity that will either confront a misconception or practice what they're expected to do when they're assessed. So if you look on your sheet, I think it's on the back page. So for me, I think about it, you're going like two ways. I would suggest maybe not trying to do both of those at the same time unless it's like a two-part type of activity. But my suggestion is to start with either, are you going to try to address a misconception and have them debunk it? Or are you going to have them practice something they need practice doing? And so those two things can be springboards for how you design your activity. Some logistics things, and based off of the questions from our last speaker, I know you guys are like professional educators because you're like, wait, that sounds good, but like, how does it really work? How do you actually do it? Because those logistics can trip you up. And at least with me, activities take way longer than you always think they will. You're like, oh, we're gonna discuss for 10 minutes. And then it's like 15 minutes later and you're like, this is really good, but we need to go. So there is going to be a little bit of timing when you're trying a new activity out, so just be mindful of that. And that's going to be something you're going to want to play in. Maybe create some flexible activities or just be mindful of being extra flexible if it's their first time doing something. And then you're also going to want to identify pre-class prep and an after-class summary, because depending on what activity you do, that may be minimal or it may be critical. So you just want to make sure that when you think of active learning in the classroom in particular, it's not just a one and done type thing. There could be things that you can do to set up to make it more meaningful. And then there can also be things that you can do on the back end to really make sure that they're driving home the point. So that was the end of where I had prepared, but I was really interested in having a discussion for the last 10 or 15 minutes that we have to really kind of come together as people who are interested and invested in active learning and see if we could share either ideas we have or brainstorm ways to overcome some obstacles. So I'd like to open the floor if anyone would have like something to ask. Yeah.
Well, one obstacle is, I really like what you said, is try to minimize in the classroom the things that you know that they can easily get on their own.
Mm-hmm.
And I've been trying to do that.
Mm-hmm.
And I will preach to them, you know, and I'd even, you know, I'll spell it out. You know, something that's just even a definition they have to read.
Mm-hmm.
So I teach mathematics. So even if it's not necessarily working out a problem, if it's just definitions, you know, the struggle is getting them to learn this on their own.
Right.
So any tips on that? Please?
Sure. So one of the things that I found is that, one, you have a lot of different types of students. So one thing that you do doesn't necessarily mean you're going to see it fixed. But there are a couple things that you can do that can meet the different needs of the different reasons why it's not happening the way you're expecting it to happen. One of the things that I do is I evaluate what it is that I'm asking them to do on their own. And one, making sure it's small. And I know that sounds kind of bad, but like making sure that it's not like read a chapter, because I don't really think that a student's going to do that. But then I also give them the objectives of like, these are the 3 things that you need to know how to do before you come in. That will help them. Another thing I think is that sometimes students think they know it, but they don't really know it. So setting up formative types of low risk or no risk assessments before they go in can help those students that are like, oh yeah, no, I got this, which we all do. And then you get in, you're like, oh, I don't got this. And so which institution are you at? At Seminole State. Okay, so I know for the UCF folks, our Center for Distributed Learning has little like personalizable widgets that are called materia that I make for all of the objectives that I call my pre-objectives, which are things that you should know before you come to class. And they're just like little games that they can manipulate stuff or like say the definitions. And it's just like really low risk. They could just play with it. And then if they can kind of self-assess whether they know that. You could do that more formally through your LMS and just say, here's a concept check, and just have what you think, like if they read it, what are the things that you want them to take away? And it could be for no points, or it could be for completion. So they have to do it, but whether they're right or wrong, they don't get points, you know, because you want them to not cheat. That's the other thing too, is like if you make it too risky, they're just going to Google the answer and put the answer that they found. They're not really going to think. So sometimes if you make it low risk or no risk, they'll be more willing to participate honestly. And from that, it's like, okay, well, if you didn't get this right, that means you didn't quite get it yet. Another strategy would be when they come in, make it to where they are going to feel a little bit disoriented having not done it. So like, for example, one of the graduate classes that I teach on teaching, I give them an article to read. And then when they come in, I give them a little quiz on the article. Now I don't then collect it and make a big thing about it. But what I do is then I use it for, they have to then categorize the types of questions as part of the activity. But when they come in, it's kind of like, oh, I don't know the answer to this. So that's another thing you could do too, because if you come in and then you just start re-lecturing everything they should have read, then the next time they're like, oh, I don't really need to read this because she's gonna re-lecture it. I don't know if any of those things would help.
I've done a couple of those.
Yeah.
Right.
Yeah. Okay.
I was going to say, one of the things that we did was start messaging to the students what our expectations were going to be for them in orientation.
Mm-hmm.
So even carrying that idea of self-directed learning, and that we're going to expect you to have done, your reading and whatnot before, but it's made a difference. And you would think that we always message it at the beginning of the class, but pulling it to orientation
kind of sets the expectation early.
Every time we do it, we reinforce it. And
Yeah.
I know there's no panacea to everything, but
Yeah.
that did help us.
That's great. Another thing I could think of too is that making something less textual and more video can also be helpful. I haven't quite gone there myself, even though that's on my to-do list, but it seems like students are also a little bit more willing to like click on a video and watch something than they would necessarily read something. So maybe if you think that could be an option, exploring different ways that you could either create short videos or find short videos or have GTAs or even as a service learning project create short videos or?
I was interested in that. I did a survey, and I always ask my online students, and they're required to reply to me once a week with something. But the majority of them, they said they didn't like watching the videos.
Okay. Well, I mean,
But that's on my field.
yeah. Yeah.
It's just so interesting. Like,
How it's different. I know that some videos are better than others.
some of the videos.
The length can be a big determining factor of how effective or how willing students are, or it could be a culture. There's a company in Florida that tends to have a lot of chemistry videos as part of a product that they're pushing, and the students overwhelmingly are buying into that company because they say the videos are so helpful, which was what prompted me to think, well, maybe am I not meeting them where they have their needs, but yeah.
Because that video is cool.
Yeah.
I wanted to watch that video.
Yeah. Yeah.
You might check, I don't know what your publisher does, but one of the things I started working on was adaptive learning, to kind of free me up from the, kind of the nuts and bolts of the stuff that they need to know, but they're not as important, for them in terms of creating and writing about their projects. I teach history, but they do need to know who is John Winthrop, but I want to talk about what he thought and believed and things like that. But so I started using the publisher's adaptive learning, and it comes for free with the ebook, and the ebook's down to $35. I mean, for history, that's
Oh, that's great.
yeah. I mean, I know there's a lot of push to go for zero cost, and maybe down the road I could go to that route. But I found it actually interesting. I started playing with it, and at times it'll drop the video in, a very short length video from the author who's a really prominent historian. If they get something wrong, it redirects them back to where they were at. It asks them to kind of bet, like how well do they know something. And of course, I'm always Vegas bound, so I bet everything. And I usually hit back to zero. But it does kind of. This first time I'm using it, so I can't speak to its success yet. But if your publisher puts out some materials like that, and I press the publisher and reps to say, look, I got to keep the cost down for these guys. What do you think is the best option to maximize the effectiveness of that textbook, so that I can be freed up to have them working on creating. My final project is a museum. They do a digital museum exhibit. They create their own and answering a final prompt. So at that point, I kind of bring together everything, my emphasis on history as a narrative, the working with sources, and the idea of the role of museum in public history. So, kind of thinking about it in multiple ways, but also giving them something down the road to create. And I know with math, that may be more difficult. I don't know.
They do have
Actually,
adaptive.
Yeah, I was going to say, the learning aids for mathematics, they almost all have to have some component for them to be
Adaptive.
Yeah.
So do they have a really good system, in place, a good adaptive?
It's not that.
Yeah.
It's gotten so much better.
And I think that's the hard part too, though, is we're looking at what are the materials that we're given, but then how do we either leverage the materials that we have access to or create our own materials to kind of put it together to make a plan. And so I'm curious as to if anybody is struggling with kind of what we were talking about today, about how they have an idea, but they're not quite sure how to turn that idea into an active learning activity. Yep.
Well, the last few years before the semester starts, I mean, the first week of actually semester, usually I require them to take a pre-test, and I tell them that they don't need to read about it. All my undergraduate classes they do that, and for graduate seminar I started very first class session after we introduce ourselves, and then I asked them a few questions about basic concepts that they should know, because they're supposedly more institutionalized than the undergrads, but it's amazing how little they know about some of the most basic stuff.
Yeah.
We don't
Yeah.
make any judgment. We just carry it as a conversation.
So I was planning on talking more about, and misconceptions, the term of preconceptions or alternate conceptions or misconceptions, there's some nuance here, so I don't mean to like lump everything into, when I say misconceptions, I'm kind of using the term loosely. But there's an idea here that like, there's a lot of reasons why people have ideas when they come in, and even if they're taught, there's a really cool documentary called Private Universe. It's from like the 80s or maybe even earlier. I think it's 80s if I can judge the hairstyles correctly. But so it's called A Private Universe, and it's a documentary where they ask Harvard graduates and faculty about the phases of the moon and what causes the seasons. And there's an overwhelming presence of misconceptions, even from people who have studied planetary science and astronomy and have a strong science background, and those who haven't, who may be focused more on the arts. And so the documentary goes back and looks at, well, what happened, where do these students think before they should have been taught this? I think in this case it was a 9th grade class. So they talk to the 9th grade students before they have the lesson. Then they show the lesson, which is a really good hands-on interactive. I mean, I think it's pretty good teaching of the lesson. And then it actually questions it has like a case study of one of the particular students afterwards. And you see that she's learning, she's getting it. But some of the misconceptions that she has still persist, even despite being present in a very well-taught environment. Mm-hmm.
You will be alarmed to learn that a more recent video that you can find shows students, and this is in one of Eric Mazur's,
Mm-hmm.
I don't know, maybe it's not Eric Mazur's, but at Harvard Physics.
Yeah.
These are undergraduates, and they were asked the same question, and these are students who have passed, physics, right?
Mm-hmm.
And they had, again,
right.
they were able.
It was like concept inventory.
Exam,
Mm-hmm. But when they talked about it.
Yes.
Yeah.
Outside of class, they went back to their old erroneous misconceptions about the Earth being closer to the sun.
Yeah, well, I would go so far. I mean, erroneous, maybe scientifically speaking, but in the contextually speaking, a lot of times these are very probable reasons why people have these. I mean, I have a 2-year-old and a 5-year-old, and I tell you what, before they can even walk, they know that getting close to where mommy's cooking is hot, but if they're back further away, that it's safer. It's just something I think that they're just incorrectly applying to another setting, and then they're not catching it, or it's so held so strongly. There's a lot of cultural implications of that too, where if you learn something from someone close to you, like let's say you ask your dad, hey, why does this happen? And he tells you something that's incorrect. But then like later on, maybe that's like harder to change because, you learned it in a way that of course, my dad can't be wrong, And so I think that there's a lot of reasons. And I think it's important too, because aside from that initial shock that we have, we're like, how do you think this? And then you start like doubting your whole profession. Like, am I doing nothing in my life? But then you have to like stop and say, okay, you know what? I'm glad I know this because now I can change it. If I didn't know this was happening, then I can't do anything about it. And so it changes the way you ask questions and the way that you look. This is not, yeah. Yeah, Sonia.
I was going to say that also feeds into what is considered System 1 or System 2 thinking by a lot of the research on how people learn. And so a lot of times people go into that System 1 thinking, which is just that like response.
Yep.
Versus if you ask them a question like that and you detail it out and they have to think through it, then that will kick in System 2 thinking, which will get them more the correct answer usually.
And with the seasons, you could say, well, it's like closer, farther away. It's like, well, if it's closer here, then why is the southern hemisphere having a different season? Then that could prompt them to be like, oh wait, maybe what I think isn't right, and they'll reevaluate it. Yeah. If I am sensing the time correctly, we have a couple more minutes. We have like 2 more minutes.
I mean, I'm already thinking of one that I could do.
Oh, go ahead, please.
In pre-calc, we do this. You take a sheet of cardboard, they're creating a box, and they have to figure out, perfect squares to cut in each corner. And I can do this in my office. When they come to my office, and we have this wonderful conversation, and back and forth. You can definitely see the active learning. In class, I have all these things I have to teach, and that's where I'm trying to figure out a way to get that out of the way. they start experimenting on, they have this misconception as, they just look at the box and they get an idea what the volume is, but then they don't realize like there's a point where the volume goes down again. So they're realizing how they're using mathematics to reach that max potential. And then the other one was, you want the volume to just be at least a certain amount, and so they realize that there's two boundaries on where you can reach that. And
do you know what I just?
I can do it in my office,
Yeah.
but in class I don't have time.
But I think that's a great example, because one of the things I really like about that is that it's simple, like in terms of the materials, and it seems like even if someone doesn't really feel like engaging in math or has some kind of hesitancy or some math phobia, that paper is really kind of non-threatening, and that you've already seen it being successful. So I think actually that is a great prompt for that. I would love to encourage you to think about how using that time might be really valuable, because the way I think of it, it's like the activity before content, content before vocabulary. And I'm pretty sure I learned that from you. Is that your thing? So I'm going to credit Kevin Yee for that, for teaching me that. Of the way of thinking about it like that is that if you have, so again, it's activity before content. So you do the activity before you say what it is, which is kind of what I was modeling here in the beginning of our session. And then content before vocabulary. So they learn the idea of it before you then name it. So we learned that volume is an additive before I said, oh, there's this thing called the conservation of mass, but that's not assumed to the, so you're kind of like coming in with an activity and then building a concept and then saying, oh, by the way, there's like, this is part of what we're learning today, and this is a thing. And what I like about that is that it has them read it differently. Because if you say, okay, read a chapter on buoyancy, and they're just reading it, there's a lot of ways that students approach reading. A lot of times it's not the most productive way unless we kind of teach them how to do that. But let's say, for example, I give you a activity and I debunk this misconception, which I'm not gonna go out just in case I ever get to do it with a few of you if I haven't done it with you before. But there's a big misconception that people have that ties into this concept of density, and it leaves most of the people, including that GTA, it was like, do you want me to tell you the answer or what I really think? Because it really does kind of get at what we think would happen. But then what it does, if you learn that and then I say, okay, now read this, you have a different mindset going in and reading that problem. You have an experience that you did that you can read it through. You have a prediction about like why did that happen, and you have like a reason to read it. So I would almost say that like something like that could almost make what you're asking them to do more valuable, because now their motivation to want to know why is it like that? Because maybe they don't want to know some kind of application that's in a book problem, but like I want to know why my paper box didn't happen the way I needed it to happen. That could really change the motivation and the intent of the other things that you built around it. Anyway, so thank you very much for coming at this session with an open mind. Thank you. I'm at the University of Central Florida. My email address is my name at ucf.edu.